Alright, so thank you for tuning in. This is lesson 2, or level 2, with the training simulator. It's kind of lesson 3 for the other video series. What we're going to be talking about today is overview of HVAC equipment and applications. And so we're looking for exposure to general overview of the various types of tasks performed by that equipment, and then several of the ways that it can be configured and combined in order to meet a specific design application. And in order to control any medium, such as air temperature or any piece of equipment, it is important to have a good understanding of the form and function of the medium and or device. The more in-depth the understanding, the more the DEC technician will have the ability to verify proper measurement and operation and troubleshoot problems. Here's a picture of a mechanical plant layout. So this would be a typical building that you might see. There's a lot of air duct. That's what we're looking at in this picture. And so there might be a cooling tower on the roof or outside. There's going to be a boiler, a chiller in various locations. And you can see the ductwork goes between the floors to the different air handlers, through diffusers, etc. Here is a water-cooled system. Cooling tower, again, can be on the roof or outside. It's going to have an evaporator, a condenser, a pump, air handlers on each floor, and water pipes running in between those. And then you get into packaged DX systems. So if it's a combined package unit, it's typically going to be a rooftop unit, right? This is what you're going to see on a rooftop. It has its heating and cooling in one package. A split DX system, you're going to have a condenser outside, and then the coils, the air handler inside, and so hence the split system, right? DX, direct expansion systems. The term direct refers to the position of the evaporator with respect to the air side loop. The term expansion refers to the method used to introduce refrigerant into the cooling coil. And finally, the last thing that I wanted to show you was a VRF system. So this is semi-new to the U.S. industry. It's been in other countries for a while now. But VRF, variable refrigerant flow, sometimes referred to as VAV, variable refrigerant volume. And so here in this picture you can see that it's a tiny pipe. It's a refrigerant line that's running in between individual indoor units. So one outdoor unit can control multiple indoor units. What's nice about this system is you can do a heating and cooling on different zones at the same time. And so I showed you air duct, a water supply, and a refrigerant line system, right? This is where it really starts to make a difference, because your typical air duct, for example, might be 12-inch by 18-inch. So you can see this rectangle box here. The water supply, let's say it's a 3-inch pipe, so a lot smaller than that ductwork, but still might be hard to maneuver around ceilings and vents. And then you get into the refrigerant line, so this can be as thin as 3/8 or 1/2-inch pipe. And now, when you're talking retrofits or new construction, you're not worried about getting in the way of other contractors or whatnot. That refrigerant line can be pretty much put anywhere. So in this slide we have key terms to know. We're going to get into those a little more in depth on the next slide. But the HVAC industry, there's a thing called creature comfort. So homeothermic creatures, people and warm-blooded animals, have 3 basic environmental needs. Keep me warm but not too warm, keep me dry but not too dry, and give me oxygen. Keep me oxygenated. Is that a word? I don't know. Preferably with fresh air. So this isn't always easy, right? Fortunately, humans have figured out several brilliant and not so brilliant ways to condition their environment. It also applies to the food storage, refrigeration. So sometimes you'll see HVAC-R, so that's where the R comes into play. So here we talked about the key words. I'm not going to dig through all these, but if you want to pause it and read through it, this starts to get into some of the HVAC terms that you're going to see constantly. Obviously this isn't all of them, but I wanted to cover some of the more common ones that you'll see. Let's talk about heating and cooling. When something is heated, thermal energy has been added. We measure that thermal energy in units called BTUs. There's a key word. There's only 2 ways to add heat to something: transformation /generation and or transfer. So transformation occurs primarily through two means, combustion or excitation. It's a technical word. Heat can also be transferred the second way by various means, including absorption, conduction, and airflow. The medium we can use to transfer heat can be air, liquid, gas, solids. So if heating is, in its most basic sense, the addition of BTUs to an object, then cooling is the loss of BTUs from an object. Yes, air has mass and therefore also can be considered an object. Since cool can't be generated, there's only one way to remove BTUs. That is through the process of transfer. Transfer can be done primarily through two means, conduction or evaporation. And the HVAC industry uses all of these methods. So getting into humidity, humidification, dehumidification methods, the average comfortable zone that we're looking for is between 40 and 60% relative humidity. So moisture can be added through a couple different ways, but here's listed a few of them. Moisture can be removed a couple of different ways. Again, you can see the different options. And so when you get a really dry humidity, 0 to 30% range, you're going to have potentially bloody noses, you're going to have really dry skin. In the winter, a lot of times it's too dry and you have to actually add humidity or water into the systems. And then when it's too humid, you start to get mold problems, you start to potentially have breathing issues, and so that's that 70 to 100%. Air quality, ventilation, CO2, indoor air quality methods. So again, I'm not going to dig through all this, but if you want to pause it, read through it, it's good information, it's good to know. Basically CO2, that's the air we breathe, and the higher that is, the worse it's going to be, right? It's going to be harder to breathe. The air becomes stale around 1,200 to 1,500 parts per million. So here we dig into the indoor air quality a little bit deeper. CO2 is an important number, but you also have gases that can pollute the air. And so why do we need to bring in fresh air? Why is it a requirement by ASHRAE and built into the sequence of operations? Because there's other things, right? There's potentially cigarette smoke, there's cooking fumes, there's body odor, there's perfume, there's cleaning solutions, and then there's gases that you may not even think about, sometimes referred to as off-gassing. There's chlorinated drinking water, there's paint and stains, there's carpet, there's vinyl flooring, construction glue. So there's a lot of things that you might not think about. These are all being released into the air as it heats and cools and settles, and there's dust, and so that's important to know, and that's why we bring in outdoor air. Hospitals and healthcare facilities are going to have specific requirements for the number of air exchanges per hour. So the good and the bad of indoor air quality. And so here we talk about some of the unknowns, or some of the ones that you might not think about as much. Some of the more dangerous ones: radon, lead, asbestos, carbon monoxide, and then you can see some of the good, right? There's filters, there's vacuums, mops, UV lights. Plants are helpful, ventilation, right? So there's ways to combat some of these bads. Here you go. You can just wear a gas mask. That's the simple solution, right? So we talked about this already, but particles in the air can cause issues. So energy conservation, we can put in these systems and we can bring this outdoor air in, but what do you do when it's 98 degrees out, humid, and you're putting a building at 72 degrees with 53% humidity? You gotta constantly cool that air, and if you keep doing that over and over and over, your electric bill is going to be pretty large. And so retention and recovery are two ways that you can reduce this. So retention is going to be obtained through passive means: insulation, thermal mass, solar gain. Can also be active, such as motors, different lighting, night setbacks, optimizations, etc. Now recovery in the past 10 to 20 years has really gone up in developed methods. And so what we're talking about here is heat pumps, heat recovery coils, heat recovery wheels. So here you can see on this slide there's a bunch of different ways that you can have tasks. There's some examples of applications. Dig into these a little bit deeper. And so we talked about recovery wheels, right? Sometimes they're referred to as ERVs, energy recovery wheels. And here I tried to show a few different pictures. The middle one here shows a recovery wheel. And if you have a chance, do some research on these. When they are operated correctly, they work really well. When they stop working or that belt breaks, they can actually cost you more money. You know, it's resistance in the line. Picture of the heat pump. Again, if you have some time, do some research. And what I'm going to really recommend is VRFs. It's kind of new to the US, like I said, but it's taken off. It's going to be a very efficient, highly active system in the future, is my bet. All right, so now we're going to get into the training simulator and dig into that a little bit. Okay, so we got this booted up, waited about 5 minutes, everything's up and running. We got our Ethernet cable plugged in. This time we're going to log in through Java. Pretty much the same, but it's going to be a little bit quicker when we start clicking on stuff. So take you to the computer side and show you that. So we're logged in here on the Java side. You can see this is a Niagara Web Startup, so it's the same thing. Okay, so we logged into the JAVA controller. Everything's hooked up. We're through Java, so it should be a little quicker today. Rooftop unit controller, we're looking at 71 degrees. Room temperature here, 71 degrees. Cooling status off, heat status off. So we're going to raise this up, or sorry, we're going to raise it down since we're in cooling status. Bring it down to 65 degrees. You saw on our computer, just clicked on, that was pretty fast. Now, here's where you get into the programming side of things. On the controller, we have a humidity of 47%. On our computer, we're actually not seeing that through the rooftop unit controller. So once you get into the programming side of things, you can actually add things in like that. But just as a test, I'm going to breathe into the slot here and see if it changes on the controller. So yeah, it's already starting to rise. It was at 47, it's at 63, 65. And so as that rises, what kind of equipment will be required to bring that back down? It's too humid, so we need to dehumidify it. So a dehumidifier would be needed in the system to bring that back down to that 40 to 60%. So on the fan coil unit controller, this one here, we're going to play with this one, look at it. Current room temperature, 74.5. On the computer, we're showing 74.3. Cooling demand, 11%. We'll raise it 1 degree. So we brought it up to a 75. We're seeing what this does on the computer screen. So it went to 0% when we bumped it up a degree. So now we just bumped it down 2 degrees. We're going to see that cooling demand percentage increase. It's not as sluggish as the web HTML browser, but it is still a little bit sluggish. So you see here we went up to 71%. Okay, so what type of output is this, analog or digital? The answer is analog. What type of heating, cooling equipment would this type of output typically operate? That'd be a fan coil, a hot water coil, duct heater, modulating gas furnace. And so next we're going to look at the CO2 indoor air quality sensor. So looking at the parts per million, we're at 555. And on the computer, showing 557. And so based on what we talked about, what's acceptable? Really, anything under 1200, you know, ideally I think we're in the 400 to 600 range, but anything under 1200 is going to be fine. So let's see what happens when I breathe on this. You can see it climbs pretty steadily. On the computer screen we just hit 900, 1000, 1400, 1500, 1900, 2000. And basically this unit's going to cap out at 2000. That's the max level. And so what would we do to bring this parts per million down? Really the best way is ventilation or outside air. Those are the only two ways to bring that parts per million down. We need to bring in new fresh air. Okay, so moving on to the VFD, we're going to turn it on. And so imagine this VFD is tied to a supply air fan motor. The desired duct pressure should be maintained at 1 inch water column, WC. So for the controller and duct pressure drops, what would we have to do to the VFD? We'd have to increase the speed, right? You can see frequency output's rising up, the speed signal input's rising up. We overshot it. What do you have to do? Obviously decrease it. To decrease it, you can see it drops down. What kind of control action did we just simulate? That'd be a PID. Okay, so now we're going to look at the actuator, the Belimo actuator, and you probably can't read it, but what kind of output does this controller require? And on the cover, it has output 2 to 10 volts. And so on the computer here, we can see signal reference input 2 volt, position feedback 0%. You can see that we're at 2.02 volts. Now if we bring this up to 50%, you see that climb to 5.62. And on the computer screen, we got 5.7. You can see the position feedback starting to rise up. And eventually that'll get to 50%. It's a little bit slow. The actuator doesn't, jerk open and close super fast. If we brought it all the way up to 100%, we're at 10.1 volt. On the computer screen, we got 10 volt. And then that position feedback would climb all the way to 100%. So what are some of the devices we would control this with this actuator? And that would be air dampers, water valves, steam valves. And then last but not least, we're going to look at the temperature probe. So it's currently at 73.3 degrees Fahrenheit. If we hold on to it, it's going to rise up. So if the controller was in cooling mode and this temperature started to rise, what would the output signal be doing as the probe temperature is rising? And so the signal output would be increasing. And what do we call this type of control action? That's a direct acting. Alright, there we have it. Another lesson down. This one was a little bit of an overview of HVAC applications, some of the different situations or scenarios you might run into in the field. The goal here was, instead of running from one room with a thermostat to another room with a controller to the roof with an air handler unit or a rooftop unit, and then running back to the JACE, the computer, we brought it all together and we show you live time exactly what's happening. Hopefully this kind of helped you get that understanding. I know this one was a little similar to the last lesson in the way we were working, but we really got to start with the basics here before we start to dive into some of the more technical stuff. So thanks for watching, subscribe, leave some comments, feedback, suggestions. I'm all ears. I'm learning this as I go, hopefully transferring this knowledge to you guys and documenting it. And they say one of the best ways to learn is to teach. And so hopefully I'm teaching you guys something. Thanks for watching. Please subscribe.